Okay, so for the first half of the lecture, I want to talk about some Bayesian framework. Okay, and also just FYI, this is not going to be on the test, so if you're not interested, you don't need to take notes. Okay, so it's just some Bayesian framework, and this is more related to some other This is some topics on deep learning framework. So it's more of a FYI thing. So it will not be on the lecture note. It will not be on midterm. So if you're not interested, or if you're, you don't need to worry about this too much. But I just want to cover, or I really want to share with this framework to you guys. Okay, and more specifically, I want to talk about variational autoencoder. Okay, so I want to use this variational autoencoder, which is a model, to introduce or to comment on some deep learning frameworks, and then it's also related to the Bayesian framework. Okay, so first of all, let me introduce some terminology, which is called the conditional probability. So here we write we write probability of A given B. This is saying that the probability of A conditional on the event B happening. And this one, I'm sure that you guys have already known, is that the joint probability for A and B divided by the marginal distribution, the one that you conditional on. Have you guys heard of Bayesian framework or all these like conditional, joint, marginal, this kind of things? Are you guys familiar with? Okay, so I'm just assuming that this is all very basic things for you guys. Would that be okay? So just for a complete picture, this is called the conditional probability. The one on the numerator is called the joint probability. So this is the probability of the event A and B. Okay, so the joint of the two events, and the denominator is called the marginal distribution of probability. Okay, so for the A with a vertical bar and then with another event B, this is something called conditional probability. And for the numerator, it's called joint probability. For the denominator, it's called marginal probability, or marginal distribution. Okay. And then we also have the Bayes formula, or the Bayes rule. This is just applying this formula here twice to obtain the Bayes theorem. Okay, so the Bayes theorem is saying the following: the probability of events B conditional on the event A is equal to the joint over the marginal. And here we rewrite the joint as the conditional multiplied by the marginal. Okay, so we essentially just applying this formula twice. Okay, so we just apply that formula twice in terms on the numerator. So we'll have this expansion and then divided by the probability that you conditional on. So you have the P of A on the denominator. Okay, so what we did is just applying the formula the second time for the numerator, and then you will obtain this formula. And this is called the Bayes theorem. And this is one of the most important components in the Bayesian framework. Okay, so there's just two formula, and one of them is just applying the same formula twice. Yeah. Okay. Again, if you're not interested in deep learning framework, then feel free to ignore this first half of the lecture. But I just want to talk about something about Bayesian. Okay. With these two formulas in mind, now I'm going to introduce variational autoencoder. Okay. So this is called variational autoencoder. Have you guys heard of this VAE framework before? I think I also mentioned here and there during the lecture. This is short for VAE. Have you guys heard of VAE before? Okay, VAE is a model for generating image, but it can be used to generating anything, but it was first invented mainly focusing on generating image. Okay, and the VAE framework performed or is implemented in the following way. So first of all, I would like to develop the objective function for training a deep learning model, a deep neural network in the VAE framework. Okay, so first of all, let's write P of x, and here x is referring to image in this case in the VAE framework, but you can write x into some other things that you want, like text, like ChatGPT, that kind of things. So here I'm just going to give you some examples, like x can be an image, like 200 something, like pixel by pixels, like a matrix as an image. So here we consider x as a random variable and then as an image. Okay, and now we just apply the formula that we just talked about. So here we have x with the joint with the z and then divided by the conditional. Okay, so what we did here is just implementing using this formula by changing the order. We have the marginal on the left hand side, and then we have the joint divided by the conditional. Okay, so just changing the order to rewrite the marginal of x. So this model, this framework, or this formula at this stage is saying that we are interested in the probability distribution for the image. Okay, and then on the right hand side, what we have added is to introduce this latent variable z. Okay, so this is called latent variable. But by using the Bayesian framework, we are able to introduce some more elements that was not from the observed data. Okay, so just to repeat what this framework is saying is that we are interested in the probability of image. Okay, that is what we usually do. We are interested, like ChatGPT is interested in the distribution for the language, for the text. Okay, so this is the marginal thing on the left-hand side. We are interested in the distribution of text or image. And then here we apply the Bayesian framework by introducing this latent variable z. Okay, and then later we will see that how this latent variable z can help us to generating image, help us to generating text. Okay, and also if you think about, have you guys all used ChatGPT before? Okay, so if you type in the same question, the ChatGPT will basically return different answer every time, but related things, right? So how it can generating similar answer but different every time, different in terms of word by word, is that they have this latent variable z. The latent variable z following a what we call a prior distribution. So whenever you draw a sample of the z, you plug into the ChatGPT, and then the ChatGPT would generating some different language or different answer to you. So that is with the help of this latent variable. So the latent variable is help you to generating similar but different in terms of word by word, that kind of answers to you. Okay, so this is how the latent variable, the z, is helping you in this generative model. Okay, by the way, do you guys know what does the G stand for? Have you guys heard of that? What does the G stand for? Generative. What does the P stand for? P-train. What does the T stand for? Sorry, who? Yes. Yeah, so the transformer is a special case or a specific model for decoder, okay? And the VAE framework also have an encoder and decoder, but ChatGPT is just a special case. It's kind of like a decoder-only framework, okay? But I just want to say that the things that I'm introducing right now is what you will see or what you are using or how the tech company are using, what the tech company are using nowadays, okay? Okay, so later we will see how the encoder and decoder show up, and that is what the ChatGPT is also using. Okay. So here, by rewriting the marginal distribution in this formulation, just by applying the formula here, we have introduced a latent variable z. Okay. And now we will use this to build our generative model. Maybe I can bring this one to here. Okay, so here x is an image or text if in the ChatGPT case, and then z is the latent variable. By rewriting the formula, we have introduced some new components. Okay, so now it's just some expansion. We take the log on the left-hand side. We will also have the log of the right-hand side. Okay, and also here I'm rewriting or reusing the Bayes theorem. So I'm going to write this as the x conditional on z multiplied by pz divided by p of z given x. Okay, so what I'm doing here is just applying the formula again on the numerator, and essentially this is just the log version of the Bayes rule. Okay, so I'm rewriting the join as a conditional multiplied by marginal. Okay, and then you can see that now by writing in this way, we introduce a marginal distribution for z. This is the prior distribution. This is the part that controls the randomness. So every time you ask the ChatGPT a same question, it will return similar answer or related answer, but different in words. And that is governed by this prior distribution, this PZ, okay? So this is the part that generating related but different answer every time, okay? Now we are going to rewrite the right-hand side by applying the log trick. So like what we introduced in the maximum likelihood estimation, the log transformation is usually changing the product or division into summation and subtraction, right? Okay, so that means we have the following on the second line. So we have the log of the px given z plus the log of the pz. Okay, and then minus the log of the pz given x. Okay, so the log transformation will transfer product and division into summation and subtraction. Okay, now I'm also going to apply another trick that we have been using, is that I plus and minus the same thing. Okay, so now I'm adding a distribution called q of z given x, and then minus the log of qz given x. So I'm adding and subtracting the same thing. So this does not alter the equal sign here, right? This is also some trick that we have been applied by manipulating the distribution in the previous lecture. So adding and minus the same thing, the equal sign still hold, but we have introduced some more component here. And just FYI, the qz given x is the encoder. Maybe I can put it here. Okay, so as a side note, qz given x is called encoder in the deep learning framework. You can think about this as how you ask the question to ChatGPT. Every time you ask a question, you just type in some word to ChatGPT, right? So you can consider this is the x, the thing that you ask. And then the encoder will encode your message, your question, into some latent component. And then this latent component will later feed into the ChatGPT, and then the ChatGPT will generating an answer. Okay? So right now the qz given x is the encoder part. So it's the part that you ask the question. Okay? Later I will introduce the decoder. The decoder is how the ChatGPT or generative model generating the answer. Okay? But here the q is the encoder. You can see that it's encoding the x into a z. Later we will have the z, you input the z and output the x. Okay? That's the decoder. But right now we introduce the encoder into this picture. Okay. After that, let's group some of the terms together in the following way. So let's continue on the equal sign. So the equal sign still hold right now. And then I'm going to group things in the following way. So we have the log of p x given z. And then adding the log of a fraction. The fraction on the numerator, we have the 1 that we introduced, the qz given x. And then in the denominator, we will have the pz given x. Okay, and then you have a minus term, you minus another fraction. So the log of the pz given, the qz given x divided by the marginal, the pz. Okay, so let me just stop at this part here. So what I'm doing is that I'm grouping, so maybe I can add one. So this is the thing that I added, I move it to the numerator, and then you have a minus pz given x, and this is the one, the part in the denominator. So let me call this the 1, okay? So these two terms the plus log of qz, I move it on the numerator. The minus the pz given x, I move it to the denominator. Okay, so this is the term that I number as 1, where it come from. And now we have the minus the log of z given x. Let me call this a 2. Okay, and this is the third term, the numerator on the third term, which I call it the number this term as 2. Okay, so this is the numerator, and then I minus in the denominator the p of z, and this is equal to adding the log of pz. I just minus the negative pz. Okay, this is the 2 in the denominator. So I'm just regrouping the things differently, but the equal sign still hold. Okay. Any question regarding the transformation here? Okay, and also just to remind you, on the left-hand side, this is still the log of px, the one that we're interested, the probability or the distribution for the x, where x is your image or your text. Okay, so the left-hand side is still the things that we are interested in. Okay. Next, we are going to take, let me write down in words. So take the expectation with respect to the encoder, the thing that we introduce. Okay. So qz given x, we're taking expectation, or for this expression here, we're now taking expectation to each of the terms. Okay, so for the left-hand side, for log of px, when we take the expectation for this with respect to the qz given x, what does that equal to? Any comments or any? So on the left-hand side, we have the log of the marginal px. And now I'm saying I'm going to take the expectation with respect to the encoder, a distribution involving the latent variable. If I take a distribution with respect to the distribution involving latent variable, what does the left-hand side equal to? Any thoughts?
Would it not stay the same?
Would it? So you were saying it would not stay the same?
Like would it stay the same?
It would stay the same?
Yeah.
Yes, exactly. Why is that?
Well, I don't think it's the value that you expect from the encoder shouldn't have to change depending on
The data.
Yeah.
The x, right? Yeah, that's exactly the answer. So if I take the expectation with respect to another latent or another variable with respect to z, it should not affecting, because on the left hand side there's no z at all. So when you take that expectation with respect to some other random thing, some other things that is not x, so it will not affecting. So that means if I take the expectation with respect to my encoder, the left hand side stay the same. Okay, so that is a key tricks in this kind of latent space model or this kind of deep learning framework. So let me just repeat. If I take the expectation with respect to this distribution involving z or another variables that is different from x, it will not alter this quantity because this is kind of not related to the x at all. So the left-hand side stay the same. But for the right-hand side, some of the terms, they are starting to involving z. So when you take the expectation, it will alternating those quantities. So let's see how it will change. So for the first one, we have this px given z. So now let's take the expectation. So again, like what we did throughout the lecture, taking the expectation, it's just like the integral, the log px given z. So this is the function, and then we multiply by the probability density function. In that case, in our case, this is the z given x under the encoder. and then this is dz. So this is how we take the expectation, right? When we have the expectation of g of x, this is from, I think probably from week 1, you will have the integral of g of x multiplied by the density function dx. Okay, so that is what we do in week 1, that we introduce the idea of expectation, right? Here, your g of x is just your log px given z. Your density function is just the one that you introduce, the encoder. Okay, so same idea, how we take the expectation in week 1, and then this is how we just take the expectation in this deep learning framework. So we're just using what we learned throughout the lecture to develop this ChatGPT or deep learning framework. Okay, so same thing as what we did before. It's just changing the notation. Okay, so that is the first thing. When we take the expectation with respect to QZ, we're changing the first term in this way. Now let's take a look how taking the expectation will affect on the second term. Okay, so we have a plus, and again, integral, the fraction. We have the Q and the P here. So let's copy that. For encoder, and then we have the PZ given X. Okay, so this is the function part multiplied by the density function Z given X dz. Okay, again, similar what we did in week 1, taking the expectation. So now this whole fraction thing, you can consider this is g of x and this is f of x in the notation in week 1. Okay, so just doing exactly what we did in week 1 to this deep learning framework. Okay, now for the third term, we have a minus and then the log of this fraction. Okay, so here minus, taking the integral log of qz given x divided by the prior pz multiplied by the density function dz. Okay, so this is the formula for taking the expectation on both sides. And then on the left-hand side, this term stays the same. So we still have an equation for the distribution or for the image or the text that you are interested in. Okay. Now let's rewrite this equation and then introduce some more statistical concepts. So we have the log of px stay the same on the left hand side equal to, so now instead of writing the integral, I'm just using the capital E referring to the expectation. So this is saying the z is following from this encoder, the density function part here, and then log of px given z. Okay, so instead of just writing as an integral, I'm just writing in the formation or in the notation of expectation, right? When we did the expectation, just integral of g of x, f of x dx, right? Minus, so here I'm going to using the third term for now. So the minus, the third term is writing in this way, okay? And this thing here also has a name. It's called the KL divergence, okay? So this is saying, so for this term here, this formulation is called the KL divergence. And then it's called the KL divergence in the following direction. So the Q of z given x comparing to the pz, okay? So this is more of a definition. So the KL divergence is defined as the log of this fraction multiplied by the density function, but this one has to be matching with your numerator, okay? So this is defined, so let me add it. This is the definition of KL divergence. So when we write it in this way, we actually introduce a KL divergence, okay? So this expression again is the definition of KL divergence. So I'm just rewriting everything in terms of expectation or KL divergence. Okay, and then for the second term here, it's also another KL divergence. So here, let's add the KL divergence. So now by looking at this expression, you will know that this is the KL divergence between QZ given X and then PZ given X. Okay, same idea. This is also a definition of the KL divergence. So QZ given X and PZ given X. Okay, so now I would just want to have a quick comment on what is it. So I think you guys are already familiar with the intuition or the interpretation for the expectation. But the question is, what is the intuition or interpretation for the KL divergence? So the KL divergence is just a measurement on about how different two distribution is. Okay, so the larger the KL divergence, that means the two distributions are very dissimilar. And then the smaller the KL divergence, it means that the two models or the two distributions are very similar to each other. And this is kind of like the driving factor how people are training deep neural network or deep model here. Okay, so the KL divergence is kind of like a expectation, or if you want, you can think of it as a penalty term. If you're minimizing this KL divergence, that means you're pushing two neural networks together to make it that they're similar. So you want to minimize the KL divergence between two neural networks. And that is how people train the this VAE framework. Okay. Any question up to this point regarding the how I grouping the terms here? Okay. Now I will introduce the last step on what is the objective function for training a VAE. So here the KL divergence, like I said, is a measurement on how different two distributions are. So KL divergence, let me write dot and let's say two distributions. This thing is always greater or equal to 0. Okay, and also here let me also add it, the order matters. So KL divergence of A given B is is different from the KL divergence of B given A. So the order matters here. Okay, but the key part is that this KL divergence is always greater than or equal to 0. So now that means I can remove one of the KL divergence out of the picture, and that will introduce the lower bound. Okay, so this is saying the lower bound of the model that we are interested is the expectation of the Z coming from your encoder log of P X given Z. So this is the first term minus the second term QZ given X and then PZ. Okay, and then I'm removing or dropping the third KL divergence from the picture. And then I no longer have the equal sign holds. Now I only have a greater or equal to. Okay, so now comparing to these two equations, this equal sign still hold with these three terms. But now I'm dropping the third KL divergence. I'm dropping a quantity that is always positive. So that means the right-hand side is always smaller than the left-hand side. Okay, and this is called the evidence lower bound. And then in short, this is called elbow. Okay. And also, this is the objective function for VAE. And then just for completeness, let me give a name to each of the terms. So QZ given x, as we introduce, this is called the encoder that we intentionally introduce to this picture. So the qz given x, as you can see, that is what we added into this picture or into this objective function. The pz given x, the px given z, the other way around, this is called a decoder. So the message, like the question that you input to ChatGPT, the ChatGPT will generate an x, and then this z, so the x is the, let's say in the context of ChatGPT, you ask a question, so that is the x that you input to ChatGPT. ChatGPT will generating an z based on your question, and then this z will later pass to the decoder, and this decoder will take in the z and then output another x as the answer to your question. Okay, so that is done through the encoder and decoder. But I'm just kind of like using this as an analogy to ChatGPT. But ChatGPT is doing some quite differently from this framework. But I'm just using the language model as an example to comment on encoder decoder. Okay, and then you have the PZ. This is called the prior. And then usually for VAE framework, where Z is just following a marginal, mu, and the isotropic Gaussian. So in most of the VAE framework, you will always see that the researchers using a multivariate normal distribution to train their VAE, in particular for the prior. Okay. Any question or comments? And this is I can pause here or providing some more comments, but if you guys are not interested, then I can just skip this part. But I just want to, yes.
Can you write down the full name of alpha?
Yes, evidence lower bound. Let me write it here. Evidence lower bound. So I think the LBO is coming from the lower bound. Yeah. This is the lower bound for the marginal distribution that you are interested in. So it's greater than or equal to. The equal sign only holds when this KL divergence, when the third KL divergence that we drop, they are equal. So that's how when they train. Okay, okay. So the elbows is referring to evidence lower bound. Maybe let me add one more component here just for the completeness. So when we write the objective function, we write the objective function in terms of the neural network parameter. So here, the neural network parameter consists of two parts. So for encoder, you have a set of neural network parameter. Let's call it theta. For the decoder, you also have another set of neural network parameter for the decoder. So that's theta and phi. And then the objective function is the negative expectation z coming from q. This q here with neural network parameter phi, z given x. And then you have the log of the p. So here, the decoder will have a parameter theta. And then this x given z. Okay? And then here, I'm writing a negative sign because I want to perform minimization. So the negative on the second term would now become a plus. And then adding the KL divergence between your encoder with neural network parameter phi, z given x, and then you want to make sure that this is very close to the prior that you set. And then in most of the literature, they set the prior into a normal, multivariate normal distribution. And this is the objective function. And now also in terms of the neural network parameter, you have two neural networks. So one for encoder, one for decoder. So that your objective function is that you want to minimize this objective function to train your encoder and decoder. So you want to perform minimization. That's why I put a negative sign in the front. If you have the plus, if you keep the original one, you are performing maximization. But in PyTorch, in those deep learning framework, you are always doing minimization. So you want to add a minus sign to make it a objective function that you want to minimize. Any question, comments? I think this concludes this part of the Bayesian framework on how this deep learning frameworks are used. And this is the objective function for VAE. Any question, comments, or not interested at all? Or yes.
What does the plus sign on the very right side of the last line you wrote represent?
The plus sign?
Yeah.
Oh, it just here, this is the evidence lower bound. So here you have the plus and here you have the minus. But when you perform the optimization, we usually do it, we want to minimize the loss function. So the loss function, like intuitively, is that the greater the loss, we want to minimize the loss. So we always treat optimization problem as a minimization problem. To perform the minimization problem, you just add a negative sign to this whole equation. So I'm at a negative sign in here. I also change the sign this to plus. So that's why it becomes a plus. Yeah. Yeah. We are minimizing the negative lower bound. Is essentially to maximizing the lower bound. When we maximizing the lower bound, it's like we're pushing this lower bound to get as close as the left-hand side, okay? Because the right-hand side is a lower bound for the left-hand side. The right-hand side is the lower bound for the left-hand side. We want to maximizing to push the lower bound as high as possible to get to our quantity of interest. But in coding or in optimization problem, we always want to minimize something, minimizing the loss function. So we're just changing the sign, adding a negative sign. We're just changing a maximization problem to a minimization problem. Yeah, it's just changing the sign to convert. Instead of pushing up, we want to pushing down. Yeah. Any question, comments? Or not interested in deep learning? But I'm sure that this is something you guys use it very often or every day, but you just don't know, maybe not familiar with how it works in the backend. Yeah.
Can you explain the encoder decoder entire thing again? Like,
Sure.
What are the X and Z again?
Sorry, what?
What are the X and Z referred to in the concept?
Sure. Okay, that's also a good question. Now, I'm just going to using image as an example because VAE is invented when they want to generate an image. Okay, so what VAE is doing is the following, or in the architecture is the following. So this is your, so in many of the early VAE paper, you will always see this kind of figures. So this is called the, let me just use encoder. So EN and then DE. So what the VAE or this objective function is doing is the following. So first of all, when you training the VAE with this objective function, evidence lower bound, is that you first input an image X, okay? And then you pass through the encoder, it will generating a Z, okay? You can consider this Z as an embedding for this image. So you have a, let's say, an image of a dog, but the Z here is kind of like an abstraction of this image, like a representation. So it kind of capturing the high level representation of this image. You just you're not using the image of the cat or dog to train the model. You're using high level representation, like the shape is very fluffy or it has 2 ears and then with some shapes or that kind of high level representation. You want to use that you want to extract that embedding. So that is the Z part. And then your decoder is that you're training the decoder that input only the Z to generating the X, let's call it X hat. And then you want to make sure that your X hat, your generating image is as close as the original image that you input here. And that is what the encoder and decoder is doing. So you want to make sure the X hat is very close to X. And then this is how the architecture for encoder and decoder. Encoder input the X, output the Z. Decoder input the Z, the high-level representation of the image output the x hat. And training with this objective function is saying that you want the x hat as close as your original image. Yeah. And then in practice, when you're using this VAE, you only use the right-hand side. You're generating z from your latent or from your prior distribution. You input your decoder, generating an image. So in the implementation part, you remove or you just throw away the encoder. You only use the decoder to generate the image. Yeah. Does that answer your question?
Yeah,
Encoder.
that makes a lot of sense. So the Z just kind of like is like kind of like the key like things that you're taking out of the image and like encode.
High level representation or feature embedding, that kind of things.
Right.
Yeah.
So it's like kind of like the features or whatever is part of the image that's kind of encoded.
Yeah. In language, it's called context. You have like a full paragraphs, but you probably just need some context to summarize the entire paragraph.
Right. Okay, yeah, that makes sense.
Yeah, your image is kind of like 500 by 500 pixel, but your encoder, your Z can be just like 10 dimension. That dense representation to represent the whole image. Like the context represent a paragraph. Your representation represent the whole image. So low dimension representation that we call it Z.
Okay, thank you.
Yeah. Question?
You mentioned ChatGPT is only a decoder.
I think people call it a decoder only, but I don't like to call it a decoder only. I mean, I think, yeah, it's just a naming thing. Yeah.
Still, it follows the same.
Not exactly. This is more like a VAE framework. I'm just using ChatGPT and language as an analogy here. Yeah. But VAE is doing, ChatGPT is totally doing something very differently. And then it's relying on the transformer. So this is the T, the transformer. But I don't want to talk about language today. Yeah. Okay. Just FYI, the course title has a Bayesian framework. Okay. In case you forget what is the title of this course. And what I'm doing here is all about the Bayesian framework. So we have this joint versus the over the marginal. We have the Bayes theorems, and then here you can see that I apply the Bayes theorems, or actually all those deep learning framework, or nowadays all those generative model, it's just an application of the Bayesian framework. Yeah. And also the Bayesian framework is included in the course title. Just want to make sure that you guys are aware of. Yeah.
And that's why many of us are taking these courses.
Hmm?
I said that's why many of us are taking these courses specifically for Bayesian
Yes.
physics.
So you can see that this generative model, this deep learning framework are using the Bayesian framework to developing this kind of ChatGPT, this image generating model, this kind of things. Yeah. Any other question before we move to another topics? Also, this is not going to be on the exam, so more of a FYI, but it's included in the, I really want to introduce you because this is nowadays tech companies are doing. Other question, comments, thoughts? Or not interested, or? Okay. No other question, let's talk about also modeling. Next, I want to talk about linear regression model. Do you guys need a break? Need a break? What about can I get a show of hand? Like need a break? Okay, maybe we'll come back in 5 minutes. So because it kind of like transform to another topics. So maybe maybe we'll come back in 5 minutes. Do you want to talk about, because I'm recording right now. Because it says, I received an email that I successfully uploaded. I received a confirmation. But you were saying you need something else?
So yeah, so because I looked it up on ChatGPT where it says that it means that even if the instructor has uploaded it,
I do approve, right?
yeah, you have to on top of that approve it.
Okay. I'll take a look at that portal again. But I did receive an email saying I successfully uploaded. So maybe I will receive an email saying I approved that.
Yes, yeah, because it's just because it's better done sooner because it's
Sure.
they always need
Like,
a lot of time.
Can you stop by after this course and then let's confirm, let's approve.
Yeah.
Hi. Yeah, you were saying you're graduating this quarter, right? Yeah. And then you were, which NLP program are you going to?
The one here.
Oh, the one here. Oh, okay, good, great. So you're going, so you're graduating this quarter. Oh, okay, congratulations. Yeah. So, I didn't know like we have I think I saw a poster somewhere. There's an NLP program, but I don't know like university will have like a NLP like a department only or a program only for NLP.
I think it's on Nebraska.
Okay. Do you know or have you looked into any courses or maybe I can also join the course?
Are you teaching one?
No, I'm not teaching. I say I also want to attend NLP courses.
Oh.
Yeah, so that I can.
Happy to hear about them. I'd be happy to hear about courses.
Oh, I also don't know. So I was just saying maybe you can tell me some more interesting courses I can also attend. So I can also learn from that professor. Yeah.
Well, I took 143 with Jeffrey Flanagan. He's pretty good as a professor.
Okay.
Kind of goes into some of the basic stuff that you just went over.
There are also some Bayesian stuff.
Yeah, like naive Bayes, like
Oh, do you know who is teaching? From my department, from stats department, or from?
in the NLP department.
Oh, okay,
I think.
I see.
It's part of the CS department,
Hmm.
I think Flanagan's officially a part of the CS department.
Ah, okay.
I know he's like the main one teaching 143. I think this year reporter was. Yeah, that's what I saw.
That's a good program to go to because I know nowadays lots of company are doing NLPs. I have also intern and so other company they are all, even my friends in the industry they are asking me to help out on something that they're all working on NLP. They're so popular nowadays. Yeah, all the tech companies. Yeah, maybe you will see me as a classmate next quarter. Yeah.
That's interesting.
Yes.
Will the midterm midterm exam be graded like before the like? Because last time it took a couple of weeks. Do you know if it'll?
Okay, I will
be,
ask.
Like at the end, like if it could be
I see.
sometime next week, so we have like an idea of our grade.
I will follow up with the TA. I haven't. The thing, there are some other people who has not finished the.
Have to take it.
Yeah. So. But I will follow up with the TA. I know this is important, and then you want to make sure that it's graded as early as possible. Yeah. But right now,
People have to take it.
And yeah, but the TA can start to grade. Okay, so now let me come back to linear regression model. So actually, after the midterm 2, after the midterm 1, you can see that we are all doing different modeling things. So the linear regression model is also trying to model some data. And have you guys heard of a linear regression model? Okay, so the linear regression model is specified in the following. So I'm writing in a vector matrix form, and then if the vector matrix multiplication, that kind of things, is not very familiar, you can just think of them in the scalar version. Okay, so here the y is usually called a response variable. One scalar that kind of things you want to predict or you want to model it. So for example, it could be some, let's say, income or something like that. Okay, so this is called a response variable, and then this is a vector of n by 1. So the n here is referring to the number of data points. So you can have, let's say, n individuals, and then each of the yi is referring to the income of that particular person. Okay, and then the x is just called the what do you guys usually call dependent variables, exploratory variable? It has all different kind of name, but just the covariance that some features of that person. So this is kind of like for example, your education background or age or something like that. So you want to use those things to predict a person's income. So the x is called the covariance. Okay, or sometimes in different textbook you will see called exploratory variables, dependent variables, or some other names. Okay, but essentially they are just a feature. And again, you have n individuals and then p features for each individuals. Okay, and then for the beta is the coefficient or the parameter that we're interested in, and this is p by 1. Okay, and then we also have the error term. Okay, and this error term is also a n by 1 vector. Okay, so you have a n by 1 for the y, and then n by p for the x multiplied by p by 1, you will also get a n by 1 column vector. And then you're adding a column vector n by 1, you will have the n by 1. So the dimension is matching here. And this is the vector matrix representation or notation. If you are interested, and we can also write this in a scalar version. So y here, a column vector, you can write it as y1, y2, and then all the way to yn. Okay, so this is a column vector for y, and then n by 1. So n individuals and then one scalar or one income for one individuals. Now for the x, you will have the following. So usually for linear regression model, you will have a column of 1 in the first column for the x matrix. Okay, so that is just what we call the intercept. And then you will have your first feature x1, which is a column that you have for everyone, and then a x2 feature number 2 for everyone, and then feature, let's say xk. Okay, so then in this case, p is just equal to k plus 1. The plus 1 is saying that you have an intercept in the front. Okay, so this is 1, and then this x1 would be the second column, x2 will be the third column, you have the kth column, but that is the pth column. Okay, so you will have k features adding another intercept, and then the intercept is usually just using a vector of 1 to represent the intercept. And then this is your matrix for x. Multiply by the coefficient. So here the beta is a vector of beta 0, beta 1, all the way to beta k. Have you guys heard of, you guys have heard of a linear regression model, right? Okay, good. So we are just talking this, we are just going to discuss this model in terms of vector matrix multiplication, but it's nothing different from what you have learned before, okay? And then adding the epsilon, the error term. Later I will comment more on these error terms. Epsilon 1, epsilon 2, and then all the way to epsilon n. That is the error term. Okay, so on the top we have the matrix vector notation, and then at the bottom I just writing in terms of all the scalar, all the entries. Okay, you have n entries, n by p entries, p by 1 entries, n by 1 entries. Okay, just entries representation. Usually for linear regression model, we impose a distribution assumption for these error terms. And we always, or we sometimes impose a normal distribution with a 0 mean and then a constant variance on each of the error term. Okay, so in vector notation, this is saying the epsilon, a column vector following a multivariate normal with dimension n, and this is a 0 column vector and then a identity multiplied by sigma squared. So again, if you forget about the identity matrix, this thing here, this is also a n by n matrix, and in terms of the entries, you have sigma squared on the diagonal, and then zeros everywhere else. So this is the sigma square identity n will look like. This is an n by n matrix. Again, in terms of the scalar, this is saying each of the epsilon I is following a unit variate normal distribution with mean 0 and then sigma square. Okay. The identity n here is just make sure that it's a matrix format, and this is just saying each of the epsilon I. So here, one of them is the epsilon I following a unit variate normal. But when you combine them into a vector, it follows a multivariate or n-dimension vector, n-dimension normal distribution. Okay, so usually this is the distributional assumption, or kind of like the, I don't want to write it down, but this is just the distribution that the people impose on these error terms. Okay, so you have the model part, some coefficient multiplied by the data or the covariates plus some error term that represent the random noise on the observed response variable that you observe. Okay, so you have your model part and then some random noise, and then that consists of your response variable. The observed data that you observe is just coming from a model that you have some noise. Okay, so this is what this model is saying, or how you should read the model. Okay. And then for deep neural network, you will have y equal to f of x plus epsilon. And this, you can add in a theta here, and that will be your neural network. Okay, just an analogy. But we are just working on a simplified version, a linear regression model. But the neural network is nothing different from this kind of a linear regression model. Okay. Okay. Now, this x multiplied by beta, you can consider as a linear function. You can consider this as f of x if you want. You input the x, and then you will output some model, some prediction from that model, and then plus a normal error noise. Okay. So now let me ask you, what is the distribution for y? Any thoughts? So x is fixed, your observed data, the data that you collect. You multiply by beta, so just a linear transformation. And then you add in the epsilon following a normal random noise. So now my question is, what is the distribution for y, the response variable, in this framework? What is the distribution for y? So the distribution for y is also a normal distribution. And then the mean is equal to x multiplied by beta, and the variance is sigma square identity. Okay, so here you have a normal random variables. What you are doing here is that you shift the normal random variable with mean 0 by a value of x beta. So epsilon follow a normal distribution with mean 0. You're shifting the y, you're shifting that mean for the epsilon by amount of x beta. So you can see that the y have a mean of x beta. And then for the variance, it's just you're shifting a normal random variable by x beta. You do not alter the variance. So you still carry over the variance for x squared identity n. So then the y is just a linear transformation of a normal random variable. So you still have the normal distribution. So I think back then we used moment-generating function to prove this. You shift the mean 0 by x beta, so you have the new mean x beta. The variance stay the same. So this is the distribution for your response variable in this linear regression framework. Okay. And then in the scalar version, this is saying each of the yi following a unit variant normal with mean of xi, the covariate for that particular x multiplied by the coefficient beta, and then sigma squared. Okay, this is the scalar version, this is the vector version. And then for the error term, this is the scalar version, this is the vector version. Okay, but the idea is that you're shifting the random noise by the amount of x beta. So the mean is x beta. Variance stay the same. And then you have the normal distribution for your response variable as well. Okay, but the normal distribution is coming from the error term. This is the distribution assumption that people impose on working on linear regression model. Okay, so in this framework, now let's talk about how we estimate the parameter. So our parameter is the beta here, and then I'm also going to use some mathematical notation, which we call arc min, or maybe you call arc max to maximize the likelihood. Okay, so arc max with respect to beta. Okay, so now we just treat the y as your general normal distributions, and then we can just write down the log likelihood. So back then we have the log likelihood is just n over 2, the log of 2 pi sigma square minus 1 over 2 sigma square. And then here, instead of the individual scalar version, the summation thing, I'm just going to write it as y minus the mu. So the mu is x beta transpose y minus x beta. Any question regarding this formula here? It's just the log likelihood of a multivariate normal. Yeah. So back then, for the scalar version, we have the summation from 1 to n. We have the yi minus the mu. Here, the mu is just the xi beta. Okay. So, and then we using the vector version instead of the summation. But in the core, they're all just the same. It's just some notational difference. How we compact or how we group the things into a vector to perform mathematical operation. Any question before we proceed on solving this problem here?
So the R max is being multiplied by
Okay, so I think the argmax can be confused if you're not familiar with. So maybe let me try to write it as just a function. Okay, so here, if you consider this is just the log likelihood of a beta. If I write it in this one, maybe it will be clear. But in mathematical formulation, people write argmax or argmin to perform the optimization to obtain the parameter. That's what I write earlier. Beta hat is equal to argmax over beta for that function. Yeah, that's just mathematical people how they write things. Yeah. But in our likelihood notation, we just use the log, the L, capital L, and then beta. That's just a different way to write the same thing. Yeah. Any question regarding the notation or the setup here? Okay, so this is how, once we recognizing your response variable following a normal distribution, you can use the likelihood framework to perform maximization. You want to maximize the log likelihood, so you can get a MLE for the beta. But I think this is not usually the way that when people introduce, I mean, when you learn the least square, or when you learn the linear regression, you probably heard of this thing called the least square estimation, or no? Or have you guys heard of a least square? Or, yeah. So this is another thing you probably when you started, but I just want to comment that it is nothing different from maximizing a log likelihood. Okay, so when you're recognizing this y following normal distribution, you can learn the parameter beta in the maximum likelihood estimation framework. Okay, and then sometimes when you learn the linear regression model, you probably learn it from the least square estimation or a least squared way. This is nothing different from the maximum likelihood, and then people is writing, well, I'm still going to write argmax. Okay, so argmin, you want to minimize the squared of the residual. Okay, and then in that framework, you are minimizing the residual in a way that is the y minus your x beta, which is your model, the prediction from your model, and then you want to square it. Okay, so in the maximum likelihood estimation, you're first recognizing this for a normal distribution, and then you maximize the likelihood. So for this objective function, you want to perform maximization over beta. When you, maybe in some of your other class, you learn the linear regression from a least square estimation. This is the residual square, okay? I think if in the scalar version, you will have the yi minus the xi beta. So this is the error. This is your model prediction. This is your observed data. When you take the difference, that's called the residual, the error part. And then you take the square. Okay, so that is the square of the error, so that you want to make sure that your error is positive. And then you want to learn your parameter by minimizing the error from your model. Okay, so I'm assuming this is how you learn your least square estimation from your other class. But here I'm saying that these two frameworks, they are essentially the same. You minimizing the residual square is essentially the same as maximizing the normal likelihood. Okay, and then the idea, actually you can directly see why this is the same. So you want to maximize the likelihood, you will end up with maximizing this part because this is the part that involving beta. You want to minimizing the residual square, you're also working on the same terms here. So you have a negative sign here, so that makes a difference whether it's maximization or minimization. But by looking at these two expressions, least square estimation is nothing different from a maximum likelihood estimation. Okay, so from this expression, you can already see that they are essentially the same thing. Okay, so which way that you choose, you will get the same result. Okay, so that's just a quick comments. Any question, thoughts on the framework or the setting here? Okay, since we already talked about maximum likelihood estimation, you can perform the same thing for the first line here. But right now, I'm going to talk about how to estimate the parameter in the least square estimation. Okay, so I'm going to use the second line here. Okay, the first line is what we did before midterm 2. Okay, so I'm going to work on least square estimation. Okay, so argmin is saying that I want to find the beta such that whatever the expression after argmin will return the lowest value. That is what argmin or argmax is saying. Argmax is saying I want to find the beta that the terms after the argmax is maximized. Argmin is saying I want to find the beta such that my right hand side is minimized. Okay, that is how to read the argmax argmin notation. Okay. So I'm going to write again, maybe. Okay, so I'm still going to borrow the capital L notation, but later I will say something else, a different meaning for this capital L. Okay, so first of all, I'm going to expanding this transpose notation here. I'm going to rewrite or expanding the quadratic form of this one. So this is saying y transpose y minus y transpose, so y transpose x beta, adding, so again, when you take the transpose, you should change the order. Beta transpose x transpose multiplied by y plus beta transpose x transpose x and beta. So this is just something to pay attention to when you work on matrix and vector multiplications. The orders matters, and also the transpose will change the shape. That's just one tricky thing that is different from working on scalar version. Okay, and now the meaning on the L is called the loss function. Okay, also as how you learn the linear regression by minimizing the residual square, and that thing is called a loss. And usually for loss function, we want to make it as smaller as possible. So you want to minimize the loss function. Okay, and here I'm just expanding the quadratic form instead of the y minus x beta transpose. So this is the same. Now I'm going to group things. So the rest is just some algebraic process. So I'm going to write it as 2 and then y transpose x beta. Because this thing, they are the same, it just one is the transpose of the other one, so I can group them together. So I think one of them is minus, so this one is minus. Yeah. So it should be minus this and then plus this. So a minus b squared is a squared minus 2ab plus b squared. Okay, so this is the minus. So you have a squared minus 2ab plus b squared. And then the b squared is the, okay, so I'm also going to write it into x beta transpose multiplied by x beta. Okay. Any question regarding any of the notation or the transpose operation here? Okay, so now to perform optimization, what do people usually do, or what we have done so far before when we want to perform some or maximizations or minimization? What should we do? Yes. What is the variables that we should take derivative with respect to? Beta, right? We're interested in the model parameter, so we should take derivative with respect to the parameter of interest. In our case, it's beta. So that means we want to find the derivative of your loss function with respect to beta. Okay, beta is our model parameter, so we want to take derivative with respect to beta. Okay, so what is the derivative of the first term with respect to beta? 0, right? It does not involve beta, it's just 0. What about the second term? Well, it's just a linear transformation, so we have 2 transpose x. So that's the constant associated with beta. What is the second one? Or what is the derivative of the third one? So here we can, so for taking derivative with respect to vector, it's nothing different from taking derivative with respect for a scalar. It's just that you need to make sure the order, the dimension is matching. So here you can think of this kind of like a square. When you take the derivative with respect to a, this is just equal to 2a. And then here the a is equal to x beta. If you want to, if taking derivative with respect to vector is a little bit confusing, you can think about the scalar version. So in this way, this is saying you should have 2 multiplied by a, in our case is x beta. But don't forget there's also a chain rule, because inside your a there is also a beta. So you need to apply the chain rule. So in that case, you will have the x transpose x multiplied by beta. Any, is this, do I need to elaborate a little bit more on how we get this one? So one way you can think about this is that you have beta transpose x transpose beta. So when you take, so this is kind of like the beta has a square if you think it as a scalar version. So you have the coefficient part, the constant part stay the same. So you have the x transpose x in the front. And then you have the beta square. When you take the derivative with respect to beta, you will have a 2 in the front and then a beta in the end. Okay? And that is how to take the derivative in the vector version. Yeah. Yes?
So it's kind of like a U substitution.
I don't think we are kind of like doing any substitution. I'm just making an analogy like how to compare the scalar version and the vector version. But right now, this is just like a, in the scalar version, like ab squared. If I want to take derivative with respect to b, this is saying this is equal to 2 multiplied by ab, and then you apply the chain rule to b, you have one copy of a. Yeah. So here, the a will be beta, the b will be the x, if in that case.
Transpose will not affect.
Sorry, what?
Transpose will not affect the derivation.
What do you mean by affect? Actually, my next step is going to talk about the transpose part. Yes.
Because XBT is XB transpose.
Okay, so that's what I'm going to discuss next. Thanks for bringing that up. So now let's examine the dimension. So the dimension for y is n by 1. When you take the transpose, it's 1 by n. The dimension for x is n by p. So in this case, that means this part of the derivative is 1 by p. But now let's take a look at the second part. You will have a x transpose, that is p by n, multiplied by n by p, and then you have a p by 1. So here you have a 1 by p in the second term, you have a p by 1 in the third term. So the dimension is not matching. So that means this is not your final answer. So I think that is exactly what you were saying or your concern. So dimension not matching. So this is not a valid operation at all at this stage. Dimension not matching. So you cannot write your gradient in this way. So what should we do? And what people usually do is just rearranging terms such that the dimension is matching. So let's see how we can match the dimension. So this is saying your derivative should be 0 minus. One way you can do it is that you do x transpose y and then plus 2 x transpose x and then beta. So if you're changing the order here, you have p by 1 plus a p by 1, then your order is matching. Yeah. So this is just the tricky part for vector multiplications, that you always want to double check your dimension. Yeah. For the scalar version, you don't need to check because it's just one number and then adding summation, multiply or division. But for the vector, it's just a one step additional. You want to check the dimension. And then if you rearrange the order in this way, all your dimensions are matching. Okay, after we calculating the gradient, what do we want to do when we perform optimization? Yeah, how do we, what do we need to do here? Set it equal to 0, right? You want to find the gradient such that the derivative is equal to 0. So set this equal to 0. So let me just call it set. Okay. So for the rest, I think it's just very straightforward. You have the 2 x transpose x beta equal to 2 copies of x transpose y you can remove the 2, and then you will have the beta hat equal to, when you move the x transpose x on the right hand side, make sure you have an inverse. Okay, so that is the division for the matrix version. Okay, so you cannot put the matrix in the denominator. That is not a thing you can do for vector and matrix. For vector and matrix, you make sure that you take an inverse of a matrix. Okay, you will have x transpose y. Okay, so this is saying, for example, a multiplied by beta is equal to b, and beta hat is equal to b over a. You can write it as a fraction when everything is scalar. But for matrix, you need to make sure this is the inverse of a matrix. So you cannot write it as the x transpose x in the denominator. You have to write it as the inverse of a matrix, and then left multiply by that. Okay, does that make sense, or do we need more elaboration on that?
How do we know which term goes first? Like
Good question. Let's think about it. So here, let me just remove the 2. We will have x transpose x beta, right, on the right hand side, on the left hand side, and then we will have x transpose y by just dropping the 2, right? Your question is, what is the order, right? Okay, so now let's left multiply x transpose x inverse, x transpose x beta. Okay, so now I left multiply by that. What is then, if I left multiply by that, I should also left multiply by on the right hand side, right? X transpose x inverse, x transpose y. Do you agree with that? I'm just left multiply by that, so I should have left multiply by that. What does this equal to? The inverse multiplied by itself. It's just identity. Multiplied by beta is beta itself, right? And then you have this term remain on the left hand side. So if you left multiply, then your inverse should stay on the left hand side, such that this beta stand as just one beta. Does that answer your question? Yeah. So whether it's on the left hand side or on the right hand side, depending on that left hand side, you want to cancel out with that remaining beta. So this should only be on the left hand side. Yeah. Yeah, that's a good question. Any other question regarding any of the operations here? I know vector matrix operations can be a little bit tricky. Okay, so this is your least square estimation for your beta. And then if you want, you can also check your dimension here. This is p by n by p, multiplied by p by n, multiplied by n by 1. You will have a column vector of p by 1. Okay, so that's matched with what we start with. When we start with the model, we have a p by 1 column vector. You can see that the result from our optimization problem from this least square estimation is also p by 1. So dimension matching with what we originally set up the problem. I think we have 10 more minutes. Okay, so I think I can finish this. Okay, next up, any question up to this point? Other question? Yes, yeah, go ahead. Yeah.
Is X transpose X always invertible? Or?
That's a good question. The short answer is no. Yeah. So for example, if your covariates, like what you're collecting for some of the individuals, if some of the columns are linear combinations of the others, then you will have that kind of not invertible situation. X transpose X is not invertible. Yeah. And then I think some people call pseudo inversion for that kind of problem, or you just drop that that features, because that feature is useless. It's a linear combination of other features. Right? The short answer is no. Yeah. And then in some of the work, people do like ridge regression. Have you heard of that? Ridge regression or lasso regression. That is kind of like giving weights to some of the features to kind of avoiding that kind of things. Or lasso is kind of like a variable selection. It kind of like you want to use this feature, not using this feature. And then that would drop that feature to avoiding that kind of things. And then for ridge regression, let me think about it. If I remember correctly, you have, it's kind of like adding like an identity matrix to your X transpose X. By adding that identity matrix will make it invertible. So ridge regression is another way, kind of like a variable selection process to avoid that the not invertible problem. Yeah, but in short answer, X transpose X is not always invertible. Yeah, but there are some other problem to solve, to alleviate that problem. Yeah, that's a very good question. Yeah. Yeah, X transpose X is always not guaranteed to invertible, but this is the closed form expression. Let's say they invertible, and then you can solve it. Yeah. If not invertible, you will need to implement some other method. Okay, so last 10 minutes, I want to discuss the following two things. Expectation of beta hat. Because we have distribution assumption, so it's valid to talk about the expectation of beta hat. Okay, so expectation of beta hat is just the expectation of X transpose X inverse X transpose Y. Okay, so my question now, or my question to you is, what is the random variable, what is constant here? Which one is Y, right? What about X? It's constant, right? The data that you collect. So once you collect the data, it's locked down. So that's a constant. So your Y is the thing that involving the distribution assumption. We also, you can also take a look what we write down here, Y following a normal distribution. So Y is a random variable, okay? Since we have random variable, it's valid to talk about expectation. Otherwise, everything is a constant, then it just expectation of constant is equal to constant. Okay, so now to evaluate this expectation, you will have X transpose X inverse X transpose. We just mentioned that this is a constant, so we can move it outside the expectation, multiply by the expectation of Y. Okay, what is the expectation of Y that we write down on the top? Just X beta, right? So that means we have X transpose X inverse X transpose multiplied by expectation of Y is equal to X beta. Okay, so you will have that, and then your X transpose X inverse will cancel out with this X transpose X. So that means you only have a beta. That is left. And this is also unbiased, but people usually don't comment on that, but expectation of beta hat is equal to beta. You can also say that it's unbiased. The trick here is to recognize what is not random, what is random variables, and then you can bring outside expectation of Y, we find it is equal to X beta on the top, bring that down, equal simplify. Now let's talk, any question regarding this? It's just how we did when we evaluated the expectation, nothing different. Okay, now let's take a look at the variance of beta. Okay, so now let's bring in the beta hat is equal to X transpose X inverse X transpose Y. And then one way to think about this is that you can think about your X transpose X inverse X transpose. This is equal to A multiplied by Y. So you can see that this is nothing than nothing different from a linear transformation of a normal random variable. If you call that equal to a, this is just equal to a multiplied by y, a linear transformation of a normal random variable. Okay, and now the a here is all involving constant term. That means we can move it outside the variance. So when we move constant term outside the variance, what should we pay attention to? Taking the square, right? And then for the scalar, for the matrix version, also maybe, okay, so notes. Variance of ay is equal to a multiplied by variance of y multiplied by a transpose. Okay, so the a transpose on the right hand side, and then in between we have the variance of y. Okay, so now apply that formula, we have the following. So x transpose x inverse x transpose variance of y multiplied by a transpose. A transpose, so we need to change the order. So we need to do the reverse order. So x transpose transpose, it just become an x. And then this thing here is symmetric, so you will still have the same thing equal to that inverse. Okay, so here I'm just applying that variance of ay is equal to a multiplied by variance of y and a transpose. And I'm calling these are a, so we have a variance of y, a transpose. Okay. And then the thing is that x transpose x is symmetric. Okay, what is the variance of y that we just mentioned on the top? So let's bring that into the formula. That is equal to sigma square identity. That is also an n by n matrix, and then the dimension will match if you want to verify. Okay, then we have this expression. Okay, so now we can rearrange and then to group the terms in the following way. First of all, sigma square is a scalar, right? It's just one number. We can move it outside or in the front, okay? And then we will have identity in the middle, but anything multiplied by identity is just that thing itself. So we will have x transpose x inverse, the x transpose from the first a, and then multiply by the x from this one, multiply by x transpose x inverse. And then for the first two x transpose x, the one with inverse and without inverse, they will reduce to identity. Also dimension of, okay, so let me ask you, what is the dimension for x transpose x? For that identity. So this thing will end up with identity, but what is the dimension here? P, right? So this is the dimension of P, so no longer n. Okay, P is the number in your column for x. Okay, but that is still identity. So multiplied by anything is that thing itself. So we will have the variance of beta is equal to sigma multiplied by that, the terms after the identity.
What happened to identity in the first
Sorry,
one?
what?
What happened to identity in first one? Identity, yeah. Sigma square identity.
Oh, anything multiplied by identity is just x. It's just itself. So this is the identity with the dimension n. Okay, but this one is p by n. So x transpose identity is x transpose. Yeah, but here it also cancels out. You will end up with identity, but this identity is dimension of p. Okay, so this one more comments before. Just one more minutes. Beta hat following a normal distribution surrounding the true variance of x transpose x. Let me ask you one more question. Why this is normal distribution? This will be our last question for today. Why this is normal distribution? Hmm? Because of what? Yes, and something else. I need one more condition. Okay, so let me point it out. Your beta hat is a linear combination of a normal random variable, and any linear transformation of a normal random variable is a normal random variable. So linear transformation. Okay. Next lecture, we will using this information to perform some other calculation. So you can see that beta hat is a linear transformation of a normal random variable. So beta hat also follow normal distribution. And then we just find out what is the mean and the variance. Okay, so that concludes our discussion today. And also this one has a dimension of p, okay? It's not dimension of n. This is the dimension of p dimension multivariate normal.